Sir, can you now share, sir?
I'll try, sir. Yes, sir. Possible for me. Yes, sir.
Yeah.
Can I share and continue, sir?
Yeah, yes.
Fine. I hope the participants are able to see my screen.
Yes,
now,
sir.
Yes, fine. I'll carry on. So we were working on renewable energy systems, in particular solar-based PV systems. Now we need to understand that the voltage levels of a PV panel and the load they are different. If we take PV panel, the input will be at let's say 12 volt is one range, 24 volt is another, and then it can go up to 60 volt or 72 volts. Whereas the load or the output, if you call this as input, if you assume that this is the input, then the output is going to be termed as the load. So the output will be at some other voltage level. Therefore, you have to have a load. I need to mention the voltage level. 120 volt, we are working on DC. So that is again another important thing that you need to consider. So these are DC voltage levels. As a result, you need to know that the standard DC voltage levels are 120 volts is one, 200 volt is another. Similarly, there is a 380 volt DC bus which is used in data centers, 380 or 400, both are almost close. Similarly, 200, 230 volt. These are voltage levels. Now, if one has to move from 12 to 120, there has to be a voltage gain of 10. This is what is called as voltage gain concept. Similarly, one can look at other voltage levels and then one can decide what is going to be the voltage level. 60 to 120 will be 2, 24 to 120 will be 5, so on and so forth. Now, the method to obtain the high voltage levels is, one method is to have a series connected configuration. That is the first method, where we connect one panel in series with the other, so on and so forth. Therefore, we get the higher DC voltage level of, let's say, 380 volt. This is what we were working on, so I will stick on to this. The drawback in series connected configuration is, suppose there is shade falling on this panel, let's say one panel, then the entire voltage level is going to come down. So that is one drawback. Shading is one drawback in series connected configuration. The next method is to have a parallel connected configuration. In that parallel connected configuration, all of us would know that in a parallel connected configuration, the voltage level is going to remain the same. Though we have shading problem, the voltage level is going to be low in parallel configuration. As a result, obtaining the high voltage level of 380 volt from an input of, let's say, 12 volt or 24 volt will be difficult in a parallel connected configuration. So this is the drawback of series and parallel connected configuration. As a result, we need to look at some arrangement, some power electronic converter, which is going to give us this voltage gain. So we now need a voltage gain. Voltage gain is required, but how do we obtain this voltage gain? Now that is where power electronic converters, I will indicate them as PE converters. Power electronic converters, they are going to be useful. They are going to be used to obtain the voltage gain. This is the basic issue. Now, in a power electronic converter, I understand that all of you are final year or third year students, which means you should have come across a course on power electronics. Therefore, you will know that there are converters which are also named as topologies, which use transformers for isolation. You might have come across electrical machines where transformers are going to be used. Now, in a transformer, there is no electrical connection between the primary and the secondary. Therefore, we call a transformer to be an isolated equipment. So, in the primary, if we use, let's say, I will just indicate a transformer like this. And at the secondary, I will have many number of turns. So, that my turns ratio is 1:n. Now, in a power electronic converter, I can have this transformer and then I can obtain voltage gain. That is going to be called as isolated topology. Use a transformer to get the voltage gain, then you name it as isolated topology. The advantage is you can have very high voltage gain because just increase the turns ratio, you can easily get that. It can transfer high power as well, and there is no connection between the primary. This is the primary side, and this is the secondary side. I'm sure you would know this. Still, I'm writing for additional clarity. And then you can actually transfer power from the secondary side to the primary side and vice versa. Therefore, you can get bidirectional power flow. That is also possible. The drawback is the circuit breaker is going to be of very high capacity because you have a large turns ratio. Therefore, the circuit breaker should also be of that much high breaking capability. This is one way by which we obtain the voltage gain. The other method is don't use a transformer at all. Just have switches and other arrangements, inductors, capacitors, and other arrangements. That's what myself, Amleshwari, and our team, that's what we have done. We were working on non-isolated topologies. Therefore, which does not have transformers. It will not have any transformer. We are just going to have coupled inductors, diodes, capacitors, etc. The difficulty is going to be interrupting large DC currents. We may not need a transformer. If at all we are going to go for a grid connected configuration, there we need isolation, and then we provide a small transformer, which is essential because in a grid, if there is a problem, then we need to separate. It is called as isolation. We need to separate. At that time alone, we need a transformer. Otherwise, it is not required. So these are the two basic methods by which we obtain high voltage gain. One is use a transformer, another one don't use a transformer. My focus, we have been working on non-isolated topologies. Therefore, I will project non-isolated topologies. Nobody is going to say that isolated is wrong, non-isolated is only, no, nothing like that. These are two different techniques, that's all. Right? Now, how do we understand, how do we start building up? So for that, I'll take up the classical boost converter. You might have come across this in power electronic course. Still, I am recollecting this very soon. You have the circuit diagram of a classical boost converter, which has an inductor, switch, diode, and a capacitor. When the switch is going to be turned on, the inductor will store energy. Fine. Can I carry on? Can I start again?
Yes, sir. Yes, sir.
Yes, fine. Okay. Now, just a quick recap of a classical boost converter and its operation. Now, we have a switch, inductor, diode, and a capacitor. When the switch is on, the inductor will store energy, but the diode is going to be off. Therefore, you need to understand that either the switch or the diode only will conduct. Similarly, when the switch is off, the stored energy on the supply, that is going to be deposited, or that is going to charge the capacitor through the diode. So energy is now being transferred from the inductor to the capacitor and vice versa, capacitor to the load, etc. Not vice versa doesn't mean C to L, but the combined energy of the inductor, stored energy in the inductor and the supply, that will be charging the capacitor. That is how we get this boost factor. Voltage gain is going to be obtained, and voltage from the input to the output is going to be enhanced or boosted. Now, the key points to be understood are that the stored energy is transferred from inductor to capacitor when the switch is off, and only the switch or the diode will conduct, but not both. So we thought we can fabricate one converter or construct one converter and then test it practically. So we had, these are the specifications, 24 to 48 volt at 96 watt, 50 kilohertz. And then if you design the inductor, you need to have a ripple current. We had chosen that to be 20% of IN. These expressions you will have in Rashid's textbook. Still, I will write some of the expressions for convenience. 1 minute, sorry. So you have the voltage gain, which is V0 by Vin. I call it as voltage gain. This is given by 1 by 1 minus duty ratio, where D is the duty ratio, which is given by on time divided by total time. And then inductance value is given by the input voltage into the duty ratio divided by the frequency multiplied by the ripple current delta IL. This is the expression. Capacitor, again, you have an expression which is given by I0 into D by switching frequency into voltage ripple here, delta VC. So this is how we design the value of inductor and capacitor. D in this case is going to be equal to 0.5. We can easily compute that. So we have to operate the switch at, we need to on it, turn it on for some time, turn it off for the same duration. That gives you D equal to 0.5. This is the converter, the photograph, where we have one input port, output port, inductor. This we got from Coilcraft. Because you are finally students, many of you, I'm just telling this, you can get it from Coilcraft. Sample inductors will be given. You can get that and then you can fabricate the board. You can get a copper clad PCB and then you can use ferric chloride solution, etch it out. That is how we did the diode and other components. Now the results which we got during testing. So this is the converter. These are the specifications photograph. First of all, we tested whether we were able to get 24 to 48. So we were in a position to obtain that. This is the input voltage V in. This green color is the output voltage V naught. This blue color, what you see over here, is voltage across the switch. So we were able to obtain, I will zoom it for your convenience. We were able to get from 24 volts, we were able to get 46.9. 1.1 volt is shortage. That shortage is because of the diode voltage drop. So that also I will write down. 1.1 volts because we have a diode. No, simple Kirchhoff's voltage law you apply and then you will get the on-state diode voltage drop as 0.7. And there will be an instance drop across the inductor and the switch on a timely basis. So you get V diode approximately equal to 0.7. That is how we end up with 46.9 instead of 48. But fine, this converter is working. That is the main thing. And then we were happy. We wanted to get 24 to 380. Remember, 380 is our objective. So we thought of pushing this converter. So when we operated, let's say D equal to 0.5, we get a voltage gain of 24 to 48. Whereas if we want 380 volts, then our D value should be very, very large. Because remember, V naught by V in, I'll write it again, is given by 1 by 1 minus duty ratio D. So if D equal to 0.8, then V naught by V in, which is voltage gain, will be somewhere close to 5 times. V naught by V in will be equal to 5. That's what we wanted to test. So we had a gate pulse. This is the gate pulse. This is the on time. The details are given here. Pulse width is 16.39 microseconds, 19.81 microseconds. You divide, it will be close to 0.83 something. This will be the value of D. Then we thought of measuring or observing current through the diode and current through the switch. Remember, when gate pulse is on, switch is going to be on. Recollect the operating principle. So what you see over here is current through the switch, I switch. Green color, what you see is current through the diode. Again, recollect that only the switch or the diode can conduct. Both cannot conduct. But what you see over here at these crisscross intervals is both currents, they are there. That is current through the diode and current through the switch. They are present when there is a crisscross, which means both diode, both the components, both the switch and the diode, they are conducting. That cannot happen. If that happens, when the switch conducts, inductor will store energy. When the diode conducts, inductor will discharge the energy. But when both conduct, inductor will get confused. It will not know what to do, whether it should charge or whether it should discharge. Therefore, output voltage will be very, very less when both conducts. This is called as extreme duty ratio operation. When duty ratio is greater than 0.8, beyond that, then it is called as extreme duty ratio operation. Extreme duty ratio operation. So this will result in V naught will reduce. So when V naught reduces, the losses will be more and the output power will get reduced. Quite obviously, efficiency will come down. These are the drawbacks of extreme duty ratio operation. So we cannot move from 24 to 380. This is very, very difficult using a conventional boost converter. This is one problem that we need to understand. Then another problem that we wanted to address is ripple current. Remember, inductor will have undulations. It will rise, it will fall, current through the inductor. So we have a term which is called as delta I, which is from the peak value, positive peak to the not positive peak, from the maximum value to minimum value, you take the difference. So that difference in current is called as delta IL, ripple. This you might have come across in Rashid also. Delta IL is given by I max minus I min. I max minus I min. So one problem that you come across now is ripple current. Delta IL is high. See, when we have a high ripple current, remember we are working for renewable energy system. So implementing peak point, implementing maximum peak power tracking, maximum power point tracking, implementing MPPT, maximum power point tracking algorithm is going to be difficult. Right? So these are some difficulties of a classical boost converter. Now, I'll just summarize that in this slide. First one is voltage gain, which is V0 by Vin, that is going to be less because of extreme duty ratio operation. Extreme duty ratio operation means D is more than 0.8. So this will lead to large voltage drop across the diode and power loss, lower efficiency. And we have input current ripple, which is going to be large because inductor current rises when the switch is on and the inductor current falls when the switch is off. So these are the problems of a classical boost converter. Now, how do we overcome these problems? That gives us converter synthesis. One more thing is power hand, because we have only one power converter, one switch, one diode. Entire power has to flow through the diode, flow through the switch, etc. So handling power is another issue. Now, how do we overcome these problems? That will give us the method or what is called as converter synthesis. Before that, is there a doubt for anybody? I've been speaking for about 30 minutes or so. Is there a doubt or things clear? I'll take 1 or 2 minutes. I'll give you 1 or 2 minutes. If you have doubts, please ask your doubts. Okay, then I'll carry on. Now, we had a large input current ripple. So to avoid that input current or reduce that input current, we go for interleaving technique. What is interleaving technique? It is having something like a sandwich, bread sandwich, no? Inside or rather between two breads, we put whatever we want. We can have cheese, we can have vegetables, we can have layer and layer of different types of cheese, etc. So that is called as a sandwich. Here, technically, we call it as interleaving. That's all. So we have an input source, and then we have a load. In between, we have a boost converter. This boost converter, if you imagine that to be the intermediate or the sauce or the cheese as a brick, then you can have many layers of that classical boost converter. This is one layer, one boost converter interfaced between the input and the output, interleaved between the input and the output. I can have another similar boost structure, connect them in parallel. You connect the load between these two structures. Let's say boost converter 2 and boost converter 1. All right. So this is now called as a two-phase interleaved boost converter. You have an input source. You have two boost converters which are similar, but they are connected in parallel. And you have the load which is supplied by both the converters which are connected in parallel. This is called as interleaving technique. Now, you can actually extend this and have n number of interleaved stages. Converter 1, converter 2, 3, etc. up to n converter. So this is now called as a n-phase interleaved boost converter. This is called as n-phase because there are n number of phases. I name it as n-phase interleaved boost converter, which I abbreviate as IPs. And how do we overcome the ripple? How do we negate the ripple? That we will see. Suppose we have a two-phase interleaved boost converter. Switch 1 and 2, they are operated with 180-degree phase shift. S1 and S2, they are operated with 180-degree phase shift. It means that when S1 is turned on at time t equal to 0, S2 will be off. After some time, when S2 is on, S1 will be off. They are going to be complementary to one another. That is called as 180-degree phase shift. Again, recollect that it is a classical boost converter. So when S1 is on, inductor current IL1 will rise. Similarly, when S2 is off, inductor current IL2 will decrease. So if we plot IL1 and IL2 over time, S1 is on, IL1 rises. So S2 is off, so IL2 drops. Therefore, the current profiles will be like this. Now, by simple Kirchhoff's current law at this node, we can observe that IN, input current, IN is going to be the sum of the inductor currents, IL1 plus IL2. So if I add these two currents, blue is IL1 and then this brown or something is IL2. So I add this, I will get a smooth current profile because the ripples, they are going to be phase shifted, they get cancelled out. This is the concept of interleaving. Now, we can have we are having two phases. So we are operating at 180-degree phase shift. Suppose we have a three-phase IBC. Sorry, I will erase that. Suppose we get or we are using a three-phase IBC, then the phase shift will be 360 degrees by 3, which will be 120 degrees. And in case of N phase, you can easily understand that the phase shift will be 360 degree by N. This is going to be the phase shift. All right. So how many number of interleaved phases can we have? Can we have 10 phases? Can we have 36 phases? The answer is a limitation. The answer is no, actually, because if you have, let's say, 36 phases, then the phase shift will be 10 degrees, which means the device is going to be conducting only 10 degrees. Quite easy to understand because in a two-phase IBC, S1 conducts for 180 degree, S2 conducts for another 180, 360 degree by 2. In a three-phase, three switches will conduct for 120 degrees. Similarly, in a 10-phase, each switch will conduct for 36 degrees. Right. So 36 degrees is just 1/10 of the entire time duration, which means we are wasting the switch. Remaining degrees, remaining 9/10 of a period, we are not using that switch. Right. So there is a limitation. The limitation is you can have only 3. Practically, you limit it to 3. This is because you need to use microcontrollers to generate gate pulses. In a microcontroller, the number of independent PWMs, that is only 3. Of course, nowadays you have FPGA processors. So you can use these FPGA processors and then you can have n number of, quite literally you can have n number of PWMs. This is possible. Still, I'm telling you, if you don't want to waste the switch, then you go for microcontrollers. Take a simple microcontroller and then you program it, get 2 pulses with a phase shift of 180 degrees and then it works. That's the way it works. Now, we wanted to test it again. So we constructed a board. Then now you will see 2 boost converters in same board. There's one boost converter, L1, S1, D1, C1. There is another boost converter which comprises of L2, S2, D2. C2 is going to be common, of course. So the output capacitor, that's a common capacitor. And then you have the input port, output port, provisions to measure current. So this is again a very small board, 3 inches cross 4 inches. This 4 cross 4 rather, 4 inches over here, another 4.5 inches over here. Very small board. Of course, I have the board in campus and I'm staying at home and then handling. If I had come to your place, then I would have carried all those converters. Don't worry. Next time or whenever I get another opportunity, I'll make sure that I bring all those things in there. Because you people need to see how the converters are fabricated rather than listening. Listening is one aspect. You get some idea, but only when you get a feel, you will understand how those things look and how do you arrange those things. Anyway, so we tested, and then remember our intention is just to overcome the ripples. Ripples should not be there. That is proven over here. The orange color waveform is the waveform for IL1. This blue color is IL2. Whatever we had come across in theory, it looks exactly the same. All right. And this waveform that you see over here is the input current I in. Absolutely no ripples. You can just check this. 480 milliamperes is the peak to peak value. Whereas two currents, they are 2.2 and 2.13. So when you add them, it will be about 4.4 milliamperes or 4.33 amperes to be precise. For this 4 ampere, it is only 480 milliamperes. Right? So maybe not even 10% or something like that. This is the reason for this 480 milliamperes. And why do we get this? Because we are testing in practice, reality, not theory, not simulation. If it was ideal, it will be a perfectly flat waveform. But in practice, you will have this small glitches because no two inductors will be perfectly identical. You are switching at this instant. So that will be a small spike. That small spike is reflected here. That is the reason for this 480 milliamperes. Otherwise, it is fine. Ripple-free input current. Right? You can call this as ripple-free or negligible ripples. Ripple-free input current. Input current. Right? This is one. And this is the proof for the voltage gain. You have 24 to 48. So this is fine. Okay. So the other inferences are, you had a large input current ripple that we were able to overcome by using interleaving technique. Voltage gain is still limited. We need to work on that. That we will do. How are we going to extend or obtain large voltage gain? One, there are several methods. I have worked on, and our team also had worked on only this 3 or 4 techniques. So I will be explaining them. Now, one is a voltage lift capacitor where we don't add any other component. We simply have a different structure. That's all. We will see them one by one. Now, we had 2 interleaved configurations. Sorry, 2 boost converters connected in interleaved configuration. That is shown over here. Now, remember that both these devices, both the structures are grounded actually. Instead of grounding them, this diode was, earlier it was grounded. Instead of that, we can actually connect it to some other device. What we will do is, what I will do now is, I will transfer this diode. This diode, I will put it over here. All right. And then here I will put a capacitor. So that structure is going to be called as voltage lift structure. That is shown over here. Remember, we had a diode here. That diode was removed and it was transferred. It was put up over here. In between, instead of connecting a wire, I'm connecting a capacitor. That's all. So I'm using only one additional component, which is C lift. As a result, you will find that between this point and this point, V0 by Vin is going to be 1 by 1 minus D. Right. Another 1 by 1 minus D over here. So across output, if you take, V0 by Vin will be 2 by 1 minus D. Because this is 1 by 1 minus D. Capacitor will have another 1 by 1 minus D between this point and this point. So totally you will have 2 by 1 minus D. So we are actually doubling the voltage gain by using only one additional capacitor. Okay. Use one additional capacitor, get 2 times the voltage gain of a classical boost converter. That technique is called as voltage lift technique. This technique that we have used is called as voltage lift technique. Fine. Now, we wanted to test this as well. Well, because you can't trust them, you can't take them as such, and then you can't believe that they will work anytime. Sometimes they may work, sometimes they may not. Therefore, have a lift capacitor. Again, the same configuration. Whatever I had drawn, the circuit will also look that way. Inductor L1, switch and capacitor. Inductor L1, switch S1. This is the lift capacitor. Inductor L2, switch S2, and then the diode D2, they are connected. Output diode is here. So this is the board arrangement. Specifications, they are now 2 times. The output voltage is now 2 times. Power rating is just 96 watts. We haven't changed it, but then it can be doubled because we are now using 2 boost converters. It can be doubled. Absolutely fine. Now the voltage gain checking 24 volts to 93.2. Fair enough. We need 96, but we are getting 93.2. Very easy to understand now. There are the component count has increased, has actually doubled compared to a classical boost converter. In a classical boost converter, we had a voltage drop of 1.1 volts. Now the voltage drop is around 2.8 volts. When you compare from 96 to 93.2, the difference, the voltage drop is 2.8 volts. So that can be compensated by slightly adjusting your duty ratio. Don't keep it at exact 0.5. You keep it at 0.51, 0.52 practically. That can be obtained. So that is how people meet the required voltage practically. Okay, they take care of the voltage drop across the devices and then they work accordingly. Microcontroller programming, small change. That is it. Right. And then ripple, because we are using interleaving, there won't be any ripple. There should not be any ripple. That is again observed over here. This is the input inductor current IL1. This is IL2. Now you will see wonderful input current without any ripples. So ripple current is just 320 milliamperes. Right. So the observations are, we are increasing the voltage gain, actually doubling the voltage gain by using lift capacitor. So C lift actually increases the voltage gain, increases the voltage gain by 2. And then ripples are now ripples, interleaving itself, we didn't have ripples. So I in ripple is not an issue that we have already overcome. Voltage gain, we are slowly doubling, we are slowly increasing. We have now doubled the voltage gain, right? This is one method. Use interleaving to eliminate the ripple. Use lift technique to double the voltage gain. Right? There is another technique where we add more number of components. This is a classical boost converter. And then a voltage multiplier cell is going to consist of 2 diodes and 2 capacitors. So we try to insert this VMC network into the boost converter. Then we get a new structure. So we have a boost converter and then one VMC over here. In fact, this is what Dr. Amleshwari was. This was her first topology using VMC. She did 3 converters. This was her first converter. So we can have one VMC, we can have one more such structure, etc. All right, ma'am had done 2 VMCs. She had taken that. Okay, fine. Now that is another method, voltage multiplier cell. Fine. Now that will again give you some voltage gain. There is another technique which is using a coupled inductor and rearranging, or you can have combination of voltage gains. That's what myself, Vijay, and our team, Amleshwari ma'am was also there. We did that. Whatever you see over here is called as a quadratic boost converter, QBC, quadratic boost converter. Remember, in an interleaved configuration, we arranged the boost converters in parallel. So we got a voltage gain of 1 by 1 minus D. Instead, if we connect one boost converter in cascade, then we get a voltage gain which is quadratic, 1 by 1 minus D into 1 by 1 minus D. It is going to be 1 by 1 minus D square. This is the voltage gain of a QBC, quadratic boost converter. Fine. This is the arrangement. You can easily now understand. L1, C1, this D2 switch. This forms one boost converter. C1 will be the source for the second stage. L2, S1, D0, and C0. Right? That is the second boost converter. So here you will have 1 by 1 minus D. And finally, that 1 by 1 minus D is acting a source for L2, S1, C0, D0. So you will have 1 by 1 minus D into 1 by 1 minus D. That is 1 by 1 minus D square. This is a quadratic boost converter. Classical, this is available in textbook. Then here again, ripple will be high. You have that ripple content problem. So that ripple can be avoided by using interleaving. So why not interleave 2 such quadratic boost converters? That was our thought process. And then we had that converter also. That is over here. And that is published as our first paper. Okay, you can take this paper and then you can read. If you want, you tell me, I'll send the material. Ma'am is also having that, so you can go through this and then you will understand. So here we are using, see, L1 and L2, they are combined in one core, that is called as a coupled inductor. So L1 L2 will form one coupled inductor. This is one coupled, I will call it as CL1. Similarly, L3 and L4 is wound on another coupled inductor, that I will name as coupled inductor 2. Voltage lift technique you. So here at this point and ground, if you take the voltage gain will be, it is a quadratic boost converter. So you will have 1 by 1 minus d the whole square, another 1 by 1 minus d the whole square between this point, 1 by 1 minus d the whole square. Then we are using C lift. So totally across this C naught, we will have 1 by plus 1 by 2 by 2 by 1 minus d the whole square. This will be the voltage gain. Right? Of this quadratic boost converter. It is called as an interleaved quadratic boost converter because we are using two QBCs in parallel. Right? Test results are also provided. So this is the converter configuration. We have two coupled inductors, CI1 and CI2. And then you have all the other devices which are arranged. Then this was tested. Remember, the voltage level that we were looking at is 380 volts. So here we are now trying to get that 24 to 38. This will be a voltage gain of around 15 times, slightly more than 15. Okay. Earlier we had a voltage gain of 2. Now we are expecting 15, 7 times more. And we were able to get that. So we had 376 volts from an input of 24. So it worked. This is the input voltage, which is 24. I'll zoom it. Now this is the input voltage 24. Then this is the output voltage 376. You get the gate pulse 16.3 for 20 microsecond 40 kilohertz. So 40 kilohertz will be 25 microsecond time period. So duty ratio will be around 0.65, I remember. Yeah, 0.65. Okay. So this is fine. This converter was working. And then that is why it was published. That's another thing. Now, because D is at 0.65, you will have ripples. That ripple is high. So this is the input current ripple. Slightly higher ripple. Slightly increased delta IL. Okay. Now, that is because of D equal to 0.65. That's fine. All right. So how do we move beyond this? What has happened? Okay. Then we wanted to check the voltage across the switch. This is voltage across switch 1. This is voltage across switch 2. You will see that the peak voltage is slightly on the higher side. I'll again zoom it for additional clarity. You will see that voltage across the switch is at 184 volts. For an output of 380, it is half. Right? This is actually higher. You should not get so high. You should not get the switch stress as so high. It should be lower. So there is another modification that we had done. This is voltage across the diodes. These things you can check from the paper because it might be, for the time being, it might be way beyond your understanding. So I'll just tell you the way we constructed the converter. I'm just telling you that we started off from a classical boost converter. Voltage gain was only 2. Beyond that, we couldn't get. So we arranged the devices, we interleaved, and then we arranged the components. We got voltage lift technique. There the voltage gain was 4, doubled. And then we had a coupled inductor, we had voltage multiplier cell. So based on the coupled inductors turns ratio, so far we haven't come across that. Based on that coupled inductor turns ratio, we are expecting more voltage gain. This is the process. This is the sequence in which we are fabricating the converter. I'll wait for some more time. Maybe I'll give you 1 or 2 minutes. Any doubts so far? Are you able to understand? Can you speak? Can you unmute and ask your questions if you have some doubts? If you have some questions.
Sir, actually, this topic is very much helpful and very good, but the students from the third years and the final years are here, sir. Yes, final years has covered the whatever the topics theoretically we have covered the buck converter, boost converter, and buck boost converter and cuck converter up to that. But the hardware synthesis and all these things are new for these students. But however, these are very much helpful to them for the for the future hardware development side. If they anyone want to go for final years.
Yes.
Yes, but it's very good, sir, that you can continue, sir.
Correct. That's right.
Yes,
therefore, I too thought of yes, sir. Sir, it says another 2 minutes, the meeting will be cut off. What is the time limit, sir? Can I take another 5-10 minutes, or should I re-log in, or what is that? How does it work?
We can recall it, sir. Another 10 minutes. No issues.
Okay, another 10 minutes. Not I need another 5 minutes, sir, because I want to tell them the practical aspect and the experimental results. That's all.
Yes, sir.
Okay, fine. Now,
sir, if it is meeting is ended within the minute, you can only re-log in and then you can continue, sir. No issue.
Okay, sir. Fine. I think anyway it will end, no, sir. It says only 1 minute, so it will end in another 1 minute or so. I'll re-log in, sir. Not an issue.
Okay.
Fine. Okay. Now, this is the way you develop converters. So, for your project work also, you can take any simple boost converter and then have some simple modifications with the help of your faculty, take some references, and then you can come out with new converters. All right. I have 2 or 3 more converters. I'll just show you and tell you the way we had simulated. With that, I'll pass on to the practical aspect. These are again test results. One is called as line voltage regulation. Another one is load voltage regulation. Because for any practical system, we are discussing renewable energy systems. The output voltage should be constant when input voltage changes or when load changes. That is the test result presented over here. Now, the next converter, we had a switch here. We stopped with this. So we got a voltage gain of only 2 by 1 minus d square. We wanted to extend that because the switches were having a very high voltage test, 50%. So we thought of introducing voltage multipliers, sir.
Yes, sir. We can share and wind up. Recollect.
Yes, sir. Sir, I need this sharing permission, sir. Sir, I need the permission to share, sir. Share my screen. Yeah.
Sir, given.
Yes, sir. Yes, no. Fine. Now, this is the next modification wherein we have a VMC connected to the secondary side. So this is another converter. You can refer this paper for additional details. I'll be presenting you the test results as well. Now, when I present the test results, focus on the way I am presenting. There will be four or 3 more than 1 parameter. Okay. So that is very, very important. Don't present only 1 parameter at a time. That won't be useful. Now, the next converter that I had presented, that I'm presenting now, is actually the cubic voltage gain. So the meaning of cubic is, so far we have come across 1 by 1 minus d square, power of 3. This will give us a voltage gain of power of 3, 1 by 1 minus d power 3. This is called as cubic voltage gain. For whatever configuration I have drawn here, this is again a lift capacitor. Therefore, the voltage gain will be 2 by 1 minus d cube, plus we have another QBC stage, quadratic boost stage. So we will have 2 by 1 minus d cube. Again, you can now see that the voltage gain has increased from 18 to 380, which is 21.11 volts. Right? And there are waveforms as well. You can check the paper and then just focus on the experimental setup. You need these things. You need a DSO, you need a power supply, microcontroller to program, and other things. So those are the important aspects. Another similar converter, which has got again a voltage gain of 2 by 1 minus d power 3 cubic boost converter. The practical arrangements. Now this inductor we had wound in our campus. Okay. So again, this is just to tell you that you can do it in your lab also, not an issue. The way we capture the practical results, this may not be possible because you need what are called as thermal imaging sensor, not sensor, camera. Thermal imaging camera. You may not have this because it's expensive and it's not required for everybody also. Research institute, they may have that. We had that, therefore we had used. You can see that the MOSFET is very, very hot. This is the hot MOSFET. Okay. So that's about the result. Special result in this slide. Now, the practical design aspect, if you want to design, you have to choose the ratings of the devices. Make sure that they are at standard voltage levels. Even when you choose your converter, beginning itself, you have to choose that your voltage level is at, let's say, standard DC voltage level, 12 volt, 24 volt, output is at 380, 120, etc. Don't take any random levels because in simulation you get that 235, 296. Don't take such random levels. You have to choose standard DC voltage levels. That's the first thing. Second thing is when you choose switches with very low on-state voltage drop so that your converter, the one which you fabricate, will be more efficient, and then the voltage and current ratings must be tight. For instance, you want a switch for theoretically you compute and then the switch rating is 48 volt. Take a switch which is going to be at 60 volt or 100 volts. Don't take 600 volt switch. Then the cost is going to be more. So that is called as tight voltage rating and current rating. Similarly, same thing is true with the diode as well. Sorry, same thing is true with the diode. And then inductor or coupled inductor, this is a specialized thing. Once you start winding, you will definitely understand. PCB is very, very important for you. When you fabricate a PCB, it is actually very simple. You just need a tray, you need an iron box, and then you need a glossy photo paper. These things are readily available. Okay, ferric chloride powder again is available from Electron Components. You can easily get them. Just use an iron box for your traces, and then you can. That is how I did. I personally did. Dr. Amleshwari knows that it is still in my cabin. Brown color stains will be there. So that is going to be very, very useful to you. Fine. Once you come out with a converter, start testing it. Start testing, fabricate the hardware. It will be interesting and useful. It is possible. More importantly, this is what I keep saying. It is possible from your lab also. You can easily do that. And when you draw the PCB track, you will need what are called as footprints. What is the dimension of the inductor? Where should you place the legs, etc.? That is technically called as a footprint. So once you know this footprint, this is available from the data sheet. I'll write it. So this is available from the data sheet. For instance, I had placed inductors. There were, I said they are from Coilcraft. You take the Coilcraft, go to Coilcraft website, and then you can obtain the data sheet of such inductors. They will give you the spacing between two legs. Use that spacing to draw the PCB. Okay. Then when you start testing, you need to keep certain things in mind. See, please understand that you need to correlate various waveforms. Never have I presented only one waveform. See, this is what people do at least during reviews. This will be time. And if they present the output voltage, it will be one stick. You will never understand how it came from. What is the input voltage? What is the gate pulse? What frequency is the gate pulse? Such things will never be there. So avoid that. You have to have a correlation between various circuit parameters. Okay, that is one thing that you need to understand. And then you need DSO or MSO, digital storage oscilloscope or mixed signal with current probes as well. That I have mentioned as correct probes. Fine. So that is how you correlate your results. And then this is one thing that I keep doing. You just list out the waveforms, jot down the list of waveforms that you need. That is the first thing that I do. I take a notepad and then I start writing down what are all the waveforms that need to be captured. And then I put the probes at various points. That is how I work. You too do the same thing. List out what are the waveforms that are required. Fine. Maximum possible thing, they must be correlated. 4 channels with correlation. This is very, 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 very important. Only then your understanding is going to be proper. Fine. And then you check the, once you start testing, check the scale, whether it is in voltage mode, current mode, and similarly image. I had the experience of putting the image in Excel sheet, and then I got only data points, not the image finally. So that is an error. Check all these things in DSO. I'm telling in DSO. And then you can use a proper microcontroller, program it, and then finally the load. Generally, we will be using a rheostat. Adjust that load setting. Gate drive, again, there are various gate driver ICs in the market. You can take them. You can start using them using a simple breadboard. So these are the essential things that you would do for carrying out the experiments. Finally, the summary, as far as this presentation is concerned, we have seen DC-DC converters. Remember, DC was the first form of electrical energy. Later on, there was war on AC and DC, and AC won because it was easy to step up and step down AC voltages at that time. Now we can step down, step up DC voltages as well, easily. That's not an issue. Now, residential loads and all other loads, they have an inbuilt AC-DC rectifier. So nowadays, the trend is moving towards DC. So there could be a day when the renewable energy can be integrated to a common DC bus, and there could be AC and DC. That's called as coexistence. So they can always be there. They can always coexist. For an industry, the trustworthiness is going to be very, very important. Whether the power converters are going to be working properly, whether they will be reliable, etc. Nowadays, the trustworthiness of power converters, reliability has been proved. So industries, they have started trusting the power converters. Fine. So that is the summary. That is how I would like to summary. On that note, I would like to say thank you for inviting me. Thanks for your patient listening. And then I'll take another 2 or 3 minutes if you have any questions. That's all from my end. Over to you.
Any doubts from you all? Anything wants to ask? Anyone? Sir, one student is having the doubt. Very good. Okay. Good morning, sir. Good morning.
Yeah, good morning, please.
I am Rakesh, sir. Sir, I am working in a project of electric vehicle design, sir. In that, I want to design a boost converter which is useful for the electric vehicle. So, could you please give me some of the key points how to design a boost converter for electric vehicles?
Rakesh, in between your voice got cut. I was not able to understand your question.
Okay, sir, I will repeat it. I am working in the project of electric vehicle design, sir.
Please go ahead.
Electric
vehicle.
I want to design a boost converter which is useful for the electric vehicles, sir. Could you please give me some of the key points how to design and which is very efficient to the EV vehicle?
Yeah, definitely. Now, what are your specifications? First, note down your specifications. That will be the first thing. Based on that, you have to choose whether that particular you said boost converter. So whether a classical boost converter would be enough or whether you need to add any other voltage gain techniques, that depends on your rating, that depends on your specifications. That is the first thing.
Yes.
Next thing would be, if you have a real electric vehicle or real space where you need to put your converter. Then you need to choose the inductors, capacitors appropriately. Because in an electric vehicle, volume is going to be less. Therefore, compact converter would be required. So that would be the second step.
Okay, sir.
Yeah.
So thank you, sir, for giving this key points. I have another design, sir. That is, in electric vehicle, many components required less amount of DC, sir. Low voltage DC application is required in electric vehicle. That is like, for example, horn and small lights, indication lights. For that, we have headlights, for example. So I am going to design that single input and multiple output DC to DC converter, sir. How can we design it, sir? In order to produce a low output. Any suggestions? Could you please?
Definitely. That's actually a good application and a thoughtful question as well. See, if you take a real car, they don't use, that is IC engine based nowadays, present day car, they don't use such complicated power electronic converters. They simply go for linear regulated supplies. That's all, because 12-volt battery is going to be there. So from 12-volt, they may need only 5-volt, or they may need 3-volt for whatever applications you are mentioning. So that will be a linear application. That's all, not a switched mode application like what we are discussing, buck boost, etc. They are switched mode. So for the low voltage, low power applications, simple linear mode regulators, they are used.
Sir, whether it depends on the ratings of the capacitor inductor, sir?
No, in a linear power supply, it doesn't play a big role. Rating of L and C, inductor and capacitor.
Thanks. Sir, thank you very much, sir. Thank you very much for your wonderful presentation. It gives a very huge impact on the design and development of hardware in power electronics. So it is definitely helpful for our final year students as well as third year students. Now, presently, actually, third year students has covered single phase AC to DC converters, sir. Single phase AC to DC converters and 3-phase AC to DC converters. And now we are going to start the choppers. Choppers. So definitely this will be helpful to third year students. Thank you very much, sir. Sir, as I told you, please visit our campus whenever you have the free time. And if you have any plan to visit the Vizag, then please come to our campus.
Sure, sir. Thank you so much. Thanks for inviting, sir. I'll make sure that I come over there, sir. Probably I'll create an opportunity, as I was mentioning earlier. If there is a conference or if there is any other FDP, let me know. I'll try to fly down there and then I'll come. Pleasure, sir. Very, very happy to be there and very happy to have met you as well, though in online mode. Happy.
Thank you. Thank you very much, sir. Thank you. Mr. Raman, please exit the. Please give the thanks of both to the sir.
Thank you, sir. Thank you for your valuable time. And since this is a 1 hour session, we are not able to give more time to you. Sorry for that. And in this 1 hour, you have given a very good lecture. As I think the students, this Rakesh, I am guiding one project for him. That is why he is asking more questions related to converters. Now he is applying for a startup, EV startup challenge. So in that he has chosen converters. Since I am, my area is converters, I have advised him to do in converters. So he has come up with 2 projects. One is a high gain boost converter for the EV application for motor controller. The other one is what he was saying, single input multi output converter. That I suggested him to check, because headlight, different microcontroller for different applications. They are using several converters for each phase. For headlight, one converter; for microcontroller, another converter. So many converters they are using. So I have suggested him to go for a single input multi output converter, which can from 48 volt to for headlight, as well as microcontroller for the other applications. Go for a single input multi output converter. I have suggested him. So he is working in that. So
excellent. If you have some doubts, get back to me. We'll try to discuss, and then we'll try to find solutions. Always a pleasure. Always happy to learn. Happy to help.
yes, sir. Yes, sir. Thank you very much, sir, for the session.
Thank you. Thanks for inviting. Best wishes. Fine.
Thank you, sir.
Thank you. Thank you so much. Later on, you try to share the recording.
Yeah.
The link, I'll try to download that.
Yes,
Fine. Thank you. On that note, I leave the meeting. Thank you, sir. Best wishes. Take care. Thank you, Amleshwari. All the best. Take care.
Thank you.